Next, we're going to extend the basic sine and cosine functions to the case of general trigonometric functions. So a general trigonometric function is a function that might look something like this. So we have f of x is equal to b plus a sine of omega x plus phi, just like that. Now this is a function that actually has 4 different parameters. So the parameters are a, b, omega, and phi. So for any particular example, a, b, omega, and phi would have a constant value, and then x would be the variable. And then each of these parameters have their own individual names. So first, let's look at what's happening inside the parentheses. So remember, those are horizontal transformations, and then what's happening outside of the function are vertical transformations. So inside, so if we just start with sine of x, what we can do is we can first shift the function by an amount phi. So we get sine of x plus phi, and then we can compress it by a factor of omega, right? Because when you do the compression or the stretch, you just multiply the variable x by the constant. On the other hand, if you stretch it or compress it first, you would transform it to sine of omega x, and then when you shift it, when you do the horizontal shift, x would be replaced by x plus something. So it should be x plus phi over omega. So if you think of the compressed graph first, you're going to be shifting the compressed graph by phi over omega. So you shift the compressed graph by phi over omega, whereas the original graph, original sine function, is shifted by phi. So that's the difference between the phi over omega and the phi. And it will make more sense once we look at just the graph and see what's happening with omega. So let's just look at this link first. So let's say we have sine of x like that. So there's pi and there's 2 pi. And this is just sine of x. Now if we replace this with sine of omega x, what we're doing is applying a horizontal compression or a horizontal stretch, depending on whether or not omega is less than or greater than 1. So suppose that omega is equal to 2, for example. Well, that would compress, so here's pi, and then there's 2 pi. So this would be sine of 2x. So this is a compression by a factor of 2. Right, so everything got kind of squeezed in like this. And then you apply a shift. So phi is a shift. And so if you look at the compressed graph, you would shift it by an amount phi over omega. So if we apply the shift next, just go like that. So this shift amount is phi over omega. Right? Because you want to scale the shift according to the scaling of the compressed graph. Whereas if you shift it first, you're just shifting by phi. So this would be a shift of phi on the original one. So you can shift it by phi first and then compress it, or compress it and then shift it by phi over omega. Either way, phi is called the phase, or sometimes it's called the phase shift. So phi is the phase. And basically what it represents is the phase of your sinusoid at the moment when x is equal to 0. So it tells you, if you're not starting perfectly at 0, it tells you the shift by which you're off. Omega, on the other hand, is called the angular frequency. And so the angular frequency basically determines the period. The period, call it capital T, is the length of time. That is, if we think of x as time instead of space. Otherwise, it's just the length of space, but length of time required for the wave to make one complete revolution. In other words, it's the amount of time required to go from 0 to 2 pi on the uncompressed picture. So going from the initial one here all the way over here. On the compressed one, it's going from here to one complete circle. So one complete revolution later, one complete cycle later, we are at pi. So for this example, sine of 2x, the period should just be pi, because we can see quite clearly that we're making one complete cycle every pi units in space, or pi units in time, depending on the context. Now there's a nice way to figure out the period based on the angular frequency, and that is my following trick, which I'll write over here. There's a little bit of space left. So the trick is, I think of omega x, so I forget about the phase shift, because the phase shift just shifts everything by a constant amount. So I'm really just thinking about from the beginning to the end of a cycle, so I'm not worried about the shifting amount, so I just think about omega x. And the idea is, I know that when you reach the period, you've made one complete cycle. Now in the original picture, one cycle is 2 pi. So what I want to do is I want to set 2 pi equal to omega times the time, whatever the time is, to make one complete cycle. And I get this relationship here. So in other words, I look at the omega x up here, and I say, okay, well, for what value of x will this equal 2 pi? So I set omega times this capital T to equal 2 pi. And you can solve it for capital T. You get capital T is equal to 2 pi over omega. So that's the relationship between the period and the angular frequency. So the period is literally 2 pi divided by the angular frequency. You can also see what that horizontal compression actually does. So the horizontal compression actually just scales time, right? So if it's a wave in time, it scales time by a factor such that the period is equal to 2 pi over omega instead of just 2 pi. Or if it's a wave in space, it scales space so that the spatial period is just 2 pi over omega. So that's exactly what omega does. So hopefully with these pictures, we understand what's happening horizontally, right? We have a shift, right? We have a compression, and then we have a shift. So the compression basically rescales time so that your period is 2 pi over omega instead of 2 pi. Notice that if omega is equal to 1, your period is equal to 2 pi. And then it shifts it. So if you don't have a traditional sine where you're starting at 0 at the center point, you want to shift it so you get a sine starting somewhere else. Okay, so that's the inside. Now let's look at what's happening actually, let's just start all the way from the beginning. So y is equal to b plus a sine of omega x plus phi. So we already saw that phi was the phase shift, and then omega is the angular frequency. If x does represent time, and normally we use t instead of x, but suppose that x represents time, so it has units of seconds. In that case, omega would literally be radians per second. So that's why they call it the angular frequency. It tells you how many radians of a circle you traverse each second in time. Or if x is length, it tells you how many radians of the circle you traverse for each meter in space. Now let's look at these vertical transformations. So first of all, we have our shifted and our scaled sine wave. So this would be sine of omega x plus phi. And it still goes between +1 and -1. So what the a and the b do is they affect what's happening vertically. So first of all, when you do a, you're multiplying the output by a factor of a. Right? So if we're multiplying it, that's going to be a vertical stretch, or a vertical compression of a is less than 1. You're literally taking it and you're multiplying everything the outputs by A. So this 1 gets multiplied by A, and you get an it's plus A and minus A. This minus 1 gets multiplied by A, and it goes to minus A. Right? 0 gets multiplied by A, and it still stays 0. This gets multiplied by A, and it's whatever. So it's basically a vertical stretch, or if A is less than 1, it's a vertical compression. So A is known as the amplitude. So A is called the amplitude. And essentially, if you have a sinusoid like this, you have a center line, and the amplitude is basically this amount right there. So that length is the amplitude. Right, because the sine wave started with an amplitude of 1, and then you stretch it vertically by a factor of A, so A is the new amplitude. And then plus B, so what are we doing next? So let's start again. So let's say we have our shifted, compressed, and stretched. So we have our amplitude A, and then minus A. Now if we add B to that, we're just taking all these outputs and adding a constant B to it. So we're lifting the whole graph up. We're copying and pasting it up here. So it's just going to go like this. Right? Everything moves up by exactly the same amount. So it's just a vertical shift. So everything is just raised up by an amount equal to B, which means the center line is now at y is equal to b. So basically here we have y is equal to b, and then the top of this peak is going to be at b plus a, and then the bottom of the graph is at b minus a. So b is the center, b plus a is the top peak, and b minus a is the bottom peak, because everything got shifted up by a factor of b. So for that reason, b is called the midline. Right? So b gives you the y value of the center of the sine wave, just like that. And that's basically everything you need to know about this general trigonometric function. And then the story is exactly the same if you use cosine instead of sine. And in fact, if you just set phi equal to pi over 2, that's essentially exactly the same as saying using cosine instead of sine and not having a phase shift. Right? A phase shift of 90 degrees turns sine into cosine, as we discussed in the last lecture.